And we're back online with this wonderful presentation leveraging machine learning for large scale anomaly detection and geospatial information systems. Today we have two wonderful co presenters. We have Travis Hansen. He is a seasoned product manager and technical specialist with nearly 2 decades of experience in wireless technologies, tower site development, and software development. And we also have Vijay Bopana. He is an accomplished AI and machine learning engineer with a strong foundation in data science, electrical engineering, and computer engineering. Um, without further ado, I'll give you guys the floor. And yeah.
All right. Thank you.
Thank you.
All right. I'm Travis Hansen, and then we have Vijay Bopana. I'm going to skip through these two and just get into what we do. So Alatrac is a platform that we developed in-house for capturing data related to inspections, specifically utility pole inspections, a lot of regulatory compliance. Within this, we have a lot of big data, just collecting over 500,000 inspections annually. Internally, created quite the task of managing the data sets and managing a large remote workforce. So Alatrac was born out of necessity and need, as there wasn't a platform that really fit the mold for what we were doing. So what's unique about our platform is we're not just a software company. We're a software company that also uses it in-house. We have a highly customizable data collection features such as dynamic form building, photo documentation, a lot of business logic, so you can govern how you're collecting your data to make sure it's coming in the way that you want it to. And throughout this, we've worked with the mobile telemetry, and we're gathering a lot of data points when it comes to asset inventory and collection. So our lead software architect, Josh Parker, created this proprietary Hound engine. And what we're doing is we're capturing tens of millions of data points from the mobile devices out in the field. We're an offline first approach. We're all the way up into the hills of Alaska. We're in northern Maine, and just about every state throughout the U.S. performing these inspections. With all the data that we're collecting from the Sound engine, it was taking a full-time GIS person or data specialist to look at the telemetry data to determine if there was any kind of anomalies in inspector pattern behavior as we're looking to create an efficient workforce. Obviously, the pressure of the economy and small to medium businesses, it is increasingly important that we're maintaining revenue and margin. And so we reached out to Milvian Group. We had an AI algorithm previously that wasn't quite producing the results that we were looking for. And so within that, we ran into a lot of issues. We have over 180 million data points in our sample data set. We had a lot of false positives, and a lot of these are due to human behavior. And there's also time drift in data. And then we're trying to figure out what are the key metrics or events that are happening that a user is taking that we didn't even want to put into a training model to determine what an anomaly is. So within that, our core function is we're a scalable inspection data collection platform. We're using AI-powered quality control and workflow optimizations. We partnered with the Milvian Group for their expert data preparation and anomaly detection. How we're using or want to use anomaly detection is how can we see something that's happening before our crews have left or whoever's using the platform has left their project. It's very expensive to roll a team from one side of the country to the next and then find out you have quality issues that you need to go back and address, and that might offer where you need to retrain. So why not try to capture these anomalies in the moment? And AI is a great tool for this. It's really good at being highly scalable. There's no influence in our data to what should be looked at, what should not be looked at. It's looking at our whole data set and population. So with the solution with Milvian Group, we definitely needed to work on the data pre-processing and working on feature engineering to improve the accuracy of our anomaly detection. And really what this comes down to is we're trying to prevent costly errors and downtime, improving our model accuracy, and giving us a competitive advantage to other inspection companies or our customers using our platform internally.
Thank you so much, Travis. So, in today's rapidly evolving tech landscape, Milvian Group stands as a trusted partner in harnessing the power of artificial intelligence. So, here at Milvian Group, we transform manufacturing flows with predictive AI that spots issues before they occur and deploy machine learning solutions that slash waste while boosting output. Our innovative sustainability program uses IoT sensors and AI to help companies achieve their environmental goals uh, while improving their bottom line. Whether healthcare, retail, or energy, our ROI-focused approach ensures that every AI solution uh, delivers like measurable results from generative AI that accelerates product design to smart algorithms that optimize supply chains. Milvian Group turns cutting-edge technology into a real business value. So, going to the next slide. So here we can see there were like potential obvious anomalous behavior. There were like multiple ways of detecting the patterns. So the patterns include multiple inspections from a single point, or inspections done like in a succession, like within 34, a bunch of inspections done in like 30, 40 minutes of time within a close proximity. Or if GPS data shows like minimal movement, and if the inspection site or the asset is behind some physical barrier, then it'll give an opportunity to like look at the review, look at the process of inspection, and so these are the potential causes of like anomalies, like quick inspections within a short of duration, and then doing the inspections and the inspections recorded from a single location instead from the proximity of the actual asset. So going to the next slide, I'm going to present the structure of the model. So here, this is the MLOps pipeline. We used AWS SageMaker to completely design the pipeline, and it includes the steps of extracting the fresh data every week and from the RDS database, and then it extracts, it cleanses, and prepares the data for performing the anomaly detection using isolation forest algorithm. So yeah, the model building is performed using the isolation random forest algorithm, and then the whole job is automated to run once every week. Uh, so going to the next slide. So the very important step in finding the anomalies here is the pre-processing. Actually, in the pre-processing step, the false flag, the cases which contribute to the false flags were removed, such as the demo, the events registered or registered by the demo emails or demo accounts, and then some events such as for example, like incomplete assessments or inspections. We removed those in the pre-processing. We eliminated those cases to reduce the false flags, and we consider only the first complete inspection as a first complete inspection to be considered towards finding out the anomalies. So we calculated the distance between the inspector and then the inspection site or asset to make sure the inspector is in in proximity to the inspection site. That's one of the features. And the other feature is the inspection time. We calculated the inspection time based on events 13 and 9, which are like inspection start and then actual save and exit of the proper save and exit of the inspection. So these two features are used to find out the anomalies. If you go to the next slide, we can see we perform the exploratory data analysis. We clean on like so here I need to like mention some some numbers. So I need to present some numbers such that so here we received the Hound system was recording around like 20,000 records per day. It's like 600,000 records per month, and we consider like a sample data set for a lot for the 6 months period, and using efficient queries, SQL queries, we were able to like get almost 400,000 plus, which is actually like close to 500,000 rows of 500,000 records of data to be considered for pre-processing. So, and we performed like cleaning and actually it's like a part of pre-processing step, and then we reduced the anomalies down. I mean, we reduced the records to be considered for anomaly detection all the way down to 80,000. And then we came up with, actually we detected like two features, and then we extracted one more feature, which is the inverse of the inspection time. So we reduced all the way down to, I mean, the records to be evaluated down to 80,000, all the way from 400,000. And then going to the next slide, so here we can see the inverse of inspection time and then distance. They're like very well correlated, and both contribute towards finding out the anomalies. For example, if the it's so in the anomaly detection, the outliers will be detected if, for example, if the feature distance, if we take the distance in miles, if the distance is too far, that means if the inspection, the distance between the inspector and then the inspection site is too far, then it will be flagged as an anomaly. And then the inspection time, if the inspection time is very less, that means if the inspection is done in like a couple of seconds, which is not possible. And then that means like the inverse of inspection time will be significantly high, and then it will be flagged as, and then it'll contribute towards finding out the anomaly. So we used these two features, distance in miles and the inverse of the inspection time. The actual inspection time was computed in seconds, and the inverse of inspection time, these two features, distance and inverse the inspection time, were used to find out the anomalies. Going to the next slide, here we can see with the isolation forests, one of the hyperparameters, which is contamination level. If we change it all the way, we change it all the way from 1% to 10%, like 1%, 2%, 5%. We tested with 1, 2, 5, and 10%. But here we can see user one, user two having like significantly high number of flags in any range of contamination. Any value of contamination. For example, if it's like 1%, 2%, 5%, or 10%, here we can see the number of flags for user two are significantly high, and then the first 5 users contribute a lot towards total flags, and we can see that. And at the end, we can see at the tail part, users 46 to 50, they're having like barely 1 or 2 flags, very less number of flags. And that too, like if we increase the contamination level. If the contamination level is very low, then we can see only few users being, few inspections, and few users are contributing towards the flags and anomalies. And also we can see user one is contributing like 1300, close to 1300 flags at a 10% contamination level. But user two is overall like he's maintaining the no, user two is maintaining the high activity, even at a low contamination level also, like user 2 is contributing 300 flags. And then going to the next slide, I'm going to show, so these are the total contamination flags and then maximum petition scores. Then here we can see the scatter plot. In the scatter plot, we can see out of 80,000 plus records or rows of data fed to the isolation forest algorithm, and then with 1% contamination, hyperparameter contamination, here we can see the total number of flags recorded as 600, close to 600, with maximum petition score is close to 0.2. But as we increase the contamination level all the way to 10%, here we can see it's significantly, almost like linearly raised to like close to almost 8,000, with the contamination level changed close with the maximum petition score changed to like 0.3. Yeah, and so that means like if you increase the contamination level, increasing the contamination level to 10%, increasing the total number of flags, as well as it's boosting the maximum decision score as well. Going to the so I'm going to hand over to Travis to present give the demo of the product and to summarize the work that we perform.
Thanks, Vijay. So on the left, what we have is an example of a pattern that we'd be looking for, something where maybe the team's not as efficient as they could be. And on the right is you're visualizing a pattern where it's very not robotic, but somebody's going from inspection point to inspection point, and there's a clear pattern, an expected order as they're moving. This is an example of an efficient inspector, somebody that's doing a lot of work. And even as we zoom out on the graph, all their actions are kind of predictable in some ways, versus the one on the left where you can visually see that there's a lot of chaos where maybe they aren't efficient. And so what we're able to do is flag, hey, this inspector is doing something a little bit different than the rest of them. So what's happening? In this example, there were some issues that actually required some additional funding from our customer due to some errors in the data sets. So there was a reason, and we may not have been alerted to that originally without having a tool like an AI detection that's determining these anomalies. So the goal of the tool is to grab the detection and then bring it to the surface. So on the right, you can see an example of visualizing these anomalies, and you're seeing some example data of seeing hotspots in projects and maybe who's performing those. And we're able to visualize these anomalies and make it easier to identify problems that we're seeing in the field. And so within that, the system's quite easy to use. We're trying to streamline that workflow, visualize the data set, because there's nothing worse than bad data. It's bad for us, it's bad for our customers, and it's bad for whoever is using the system. So whatever we can do to make the system that much more efficient, reduce liability, reduce risk. This is a lot of regulatory compliance and inspections. So by having these tools in the back end, we're just helping validating every piece of the inspection, whether it's somebody in the field that's doing the quality control work or flagging anomalies for users of the systems. And we designed the software to protect ourselves and protect the customers that are using it. So with Alatrac, we want to help you boost your revenue, reduce risk, and enhance your data integrity. And by bringing AI into it and doing the near real-time anomaly detection, it really increases the amount of awareness that we get and the reduction in workforce that it takes to identify these anomalies. It's a proactive approach versus reactive when it comes down the road, which is a great thing as a product, or not a product manager, but a project manager, being able to see your workforce and see these things that are happening in real time. And then lastly, Milvian coming in, they took what we had originally in our original algorithm and they improved it greatly to where we could really hone in on areas that required retraining, and additional focus to improve that revenue, and data accuracy. And without Milvian Group coming in, we were just getting inundated with false flags. And that's one of the issues with AI. And it's quite understated. And I think a lot of things when we see it in the media, we see that AI is this really powerful tool and it does a lot of great things, but it can also create a lot of false flags for you as well if it's not done properly. And that's where Milvian really stepped in and helped us out in a big way. And that is the end of our slides.
Wonderful. Thank you very much, Travis and VJ. I do have a few questions for you. Prior to this, there were a lot of manual coordination efforts. Inspectors were going out on field, but there was no clear way of managing all this chaos. What has been some of the on-ground response to implementing this from the technicians, from the repairmen? What's been the overall sentiment from this solution?
Yeah, so I mean, honestly, I believe that especially with the AI, it just creates more accountability. I mean, there's just another something that's watching them. I mean, with having a large remote workforce all over the country, companies like ours and others that use the platform, managing inspections with where you're incentivized to get quite a few done. There can be inefficiencies in that process, and what this is doing is it's creating that accountability. They know that there's also a robot watching them and checking out what they're doing. So I think the response overall has been really well taken with both the team and the managers.
And as a result of rolling this solution out, has there been any subsequent requests for extending this into other areas or use cases?
Oh, sure. Yeah, I mean, the power of this tool, looking long term, there is additional requests. I mean, whether it's just looking at the inspection data itself and determining anomalies within the data that's being brought in to help for another quality control check, just versus the telemetry that we're doing right now. There's been requests like that.
VJ, what were some of the concerns that you had when you initially started tackling this project and looking for ways to reduce the noise in those signals?
The main thing which contributes to the success of this project is understanding each and every scenario of like how it works and understanding the data. I would simply say understanding the data. That helped a lot actually. So Travis Hansen, is from Alatrac. He explained me like all the scenarios, like which one would be treated as a false flag, which case should be treated as a actual flag. I mean, actual anomaly. We figured out a lot of cases. Actually, that interaction and exchanging the knowledge of like how things work, how inspections work. That helped a lot to achieve the success of achieve the success or like reaching the end goal of this project actually.
It's usually a rare scenario where business representation and technical representation meet and work together so complementary wise, like in this situation. Can you tell us a little bit about some of the initial attempts at finding alignment between those two sides, especially since it's two different organizations collaborating in this isolated use case?
When I first received like certain documentation with like bunch of words and stuff, but even though it has like so much data in it, like I couldn't be able to like really capture what's going on in the field actually. Interacting with Travis, that helped a lot. Like he was like kept explaining me. I started like a baseline model, like baseline like a initial pipeline. Slowly, I was like optimizing it day by day, week by week. So that interaction was helping me. That helped me actually, achieve the success rate. Day by day, our success rate was like getting higher and higher. I would highly suggest. I would say the main contribution towards product success is that interaction, and then if there is any misunderstanding, if the system is flagging wrong, if it's flagging wrong, if it's throwing some false flags, and I was explaining it to Travis, and then I was like, it was at the time it was verifying everything using the Alatrac system, actually, whether it's true or not, why it's a true flag or why it's a false flag, why. We delve deep into the data, actually. We spend most of the times on data. I think AI and ML world, the data rules everything. If you understand the data, if you know each and every aspect of the data, every corner of what's going on, actually, then that helps a lot. That's the major contribution towards a successful delivery of the project, kind of. Yeah, I would say.
Yeah, no, I would agree. The data set's very complex, and then understanding how it relates to the machine learning and what should be put in it was probably the biggest challenge that VJ and I had, and taking that deep dive and going through what we'd already originally whittled down for our first attempt at AI. And then him coming in was imperative, because human behavior is not predictable. I think that's, when you're looking at a machine telemetry off a machine, if you're seeing a weird vibration, you might assume that a bolt's loose, or that a bearing is going out, or something's causing some vibration. That's an anomaly. But when it comes to human pattern behavior, it's a different element completely to throw into the model. And so, without working with VJ and refining our data sets and approaches, and finding out like what in the telemetry, we capture events, like what set of events or series of events would equate to something that maybe we shouldn't rate as high because it's not as important. Or this is something we should be looking at because this is more likely of an anomaly. And without that, that's why our first attempt failed, and when we had all those false flags. And so bringing in somebody like Milvian Group that really wants to get into the data and work with us, it was imperative to success.
Looking back now that you've completed this phase of the project, are there any particular artifacts or techniques that you would have employed earlier on to make this an easier experience for both sides?
I think with Milvian Group, we kind of knew where we were at, but I think just going into it, anytime you're entering into a project, just understanding your data set before you even hand it off to somebody to work on a model. I think that is probably one of the biggest things, and it's really hard if you're not a technical person to understand that. But really going through and doing a storyboard of what would be the expected behavior, and having that well established before you even attempt, to build out an AI project, because that alone was a little overwhelming, to be honest, when we first started, and just understanding AI. So that was one of the things I would do different.
Any last points on that, VJ?
I would say understanding the data is it's very essential for a successful AI ML project. Any kind of data, whether it's like text data, voice data, or video data, understanding the data is key in the success of any AI ML project.
I guess a subsequent question to that is, how do you verify the sanctity, the validity of the data that you are actually engaging with? Is it good data, or is it absolutely toxic spill, not radioactive data? How do you know the difference?
We start with the baseline model, and then when I started with the baseline model, it was throwing some flags. I tried using. I did some research on different multiple algorithms, and I chose like isolation forest algorithm because we have like a big set of data. And then after that, when I got the first set of results, and I discussed with Travis, and then it's called, I forgot the term, but it's like a continuous improvement, day by day. Like we were keep discussing about the results, quickly implementing it, and keep discussing the results, and then testing just validating the results by checking with the Alatrac's system, Alatrac.
Yeah, it was like having a full-time GIS persons analyzing spatial data, and every time that VJ would produce a result, we would have to take a subset or a series of those data points and do the full analysis and bring every data point, model it on a map, pull the inspection data points to see what pattern behavior was doing, inputting data into the inspection to determine, like, is this anomalous behavior or is this something that would be expected? And it took a lot of time. That was most of the work. And besides the data prep, every iteration of his algorithm going into that iForest training model was substantial in the amount of effort that it took. And to be quite honest, though, that was the amount of effort it would took anyways to determine, looking at data, determining if it was anomalous or not. So, and now there's a lot less of that, and these things are being brought up, but the process was kind of the same as manually doing it.
Well, Travis, VJ, it's been a great getting a rundown on the work that you've done recently. We're going to take a brief break, approximately 20 minutes, and then we're going to jump into the panel discussion. So with that being said, stay tuned, and we'll be back with more.
Thank you, Shaka.
Thank you.
Thank you, Travis.